Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Centrifugal Separations Part 2. In the previous lecture on centrifugal separations, we have seen a few basic concepts of centrifugal separations. We have also seen the importance of the neutral zone, and then we have also discussed a few types of centrifugal separation equipment. This lecture we will be discussing working principles of the centrifugal separations and then a few problems. Then we also see a few details about the cyclone separators as well as the hydrocyclones. Principles of centrifugal sedimentation. Let us assume that you have a solution which is having a few particles, fine particles, and then the separation of those particles by sedimentation settling is going to take a long time. Under such conditions, what you do, you prefer to go for a kind of centrifugal sedimentation. So, for such kind of solutions, if you are doing a kind of a separation by centrifugation, then let us assume this schematic is like this. So, we have a kind of a centrifugal ball of the size like this. The centrifugal ball height is B and then radius is R2, and this is the central axis or the axis of rotation of this ball, right. So, assume this ball is rotating with the central axis. Central axis is the axis of rotation, and then feed is entering from the bottom like this, and then clear liquid is discharged from the top continuously from here as shown here in the picture, right. Now, whatever the feed is coming in, that is having particles also. Those particles, those small particles, fine particles, we are separating by centrifugal force, by applying centrifugal force. This ball is rotating at certain angular velocity. Okay. So, now what we are doing, we are taking the feed and then allowing this feed to enter from the bottom, and then we are rotating it, so that the clear liquid surface we can see here. So, the liquid surface is of radius R1, right. So, when we centrifuge it, so if you rotate at very high speeds, what happens, the liquid surface will form a kind of almost concentric cylindrical surface like that, that we have already seen here in the previous lecture. So, that liquid surface of liquid is at R1 distance from the axis of rotation or from the central axis. Okay. Now, this feed that is entering at the bottom, okay, and then assume that the bottom the liquid is traveling upward, right, traveling upward. So, this feed is liquid feed is also having a particle, and then whatever the particles are there, they try to settle towards the wall and then being separated from the liquid. That is what the purpose. Let us assume a particle at this location RA is the distance from the axis of rotation. At that particular point, the particle is there, and then this liquid within the centrifugal ball, what happens, the feed is continuously coming and then the liquid is also continuously going out. It is a kind of continuous process. So, there is a kind of a residence time for the liquid, right. So, within that residence time of liquid, the particle, let us assume it reaches some other location, that location is at distance RB from axis of rotation, right. So, now this residence time is going to limit the separation, right. So, within this residence time, if RB is equals to R2, then particle will be hitting the wall of the ball and being separated. Okay. If RB is less than R2, then that will be carried away along with the liquid. So, that separation will not take place. So, separation of the particle is now based on the whatever the liquid residence time. So, we have to provide a specific volumetric rate. Okay. Okay, we have to provide a specific volumetric rate so that to get a required separation. So, how much this volumetric flow rate that we have to get. So, for that we need to know volume of the liquid. So, the volume of the liquid is nothing but pi b R2 square minus R1 square, right, because now this is the liquid is only in this part, right. So, because that is now forming a concentric surface, a cylindrical surface within the ball because of the rotation. So, now the volume of the liquid is nothing but pi b R2 square minus R1 square. If you know the residence time, let us say Tt, right, then you can know the volumetric flow rate, required volumetric flow rate for the separation of the particle, right. So, for that we have to know what we do some kind of simplification to get this residence time, okay, this residence time, and then divide this volume of the liquid by this residence time to get this required flow rate, right. And then this required flow rate will also be a function of a kind of some kind of cut diameter. It is not that you provide a kind of flow rate, all the particle will be separated, because the liquid is having particles of very wide size distribution. Not necessary that all the particles that are present in the liquid which we are going to separate by centrifugation, they will not be having a uniform size and shape. So, different shape, different size would be there. So, based on the size distribution, we will also find out the cut diameter of the particles, right. Having the diameter smaller than that one, they will be retained in the liquid. The particles having the size larger than that DPC or the cut diameter will be hit to the wall, and then they will be separated, right. So, corresponding to the cut diameter, which size particles are the will find a kind of a minimum size of the particles, that will damn sure be hitting the wall and being separated. So, obviously, the particles which are larger than that particular size will also be hitting the wall and then being separated. So, corresponding to that cut diameter, we call it cut diameter. So, corresponding to that one also we will find out what is the volumetric flow rate. So, finally, this is what we are going to do. We are going to find out a critical volumetric flow rate kind of thing, right. So, if you maintain that one, so the particles of a certain size or larger will definitely be separated, and then particles of size smaller than that one, they will be retained in the liquid. So, that is what we are going to do. So, that is what we have to do. How much volumetric flow rate we have to provide for in a given centrifugal ball, so that particle of specified size can be removed, and then particles smaller than that specified size will be carried away in the liquid, so that we can get the performance, right. So, this equation will also be applicable in other way also. Let us say you have a kind of liquid which is having particle size, let us say 0.1 to 10 micron size, right. So, then if you want like all the particles having size greater than 1 or greater than 1 micron should be separated. So, then DPC, that cut diameter, you can take 1, and then correspondingly you can back calculate what should be the volumetric flow rate that you should provide, okay. Either way you can find out. If you have the fixed volumetric flow rate, then what should be the cut diameter above which all the particle will be separated, that way also you can do the calculations, that way also you can use the same equations, okay. So, now what are we going to do here? We are deriving these equations, required equations here, and then doing some example problems, okay. Consider a volume of liquid in centrifugal ball. Feed is at the bottom and then liquid discharge is at the top. Assume that all liquid moves upward through the ball at a constant velocity, carrying solid particles with it, but the trajectory of the particle would be like this because of the centrifugal force. Because of the centrifugal force, the trajectory of the particle would be like this, because this trajectory we have already derived, we have derived it as a kind of a parabola. So, this kind of a trajectory particle will have, okay. Particles begins to settle at bottom of the ball at some position in the liquid, say at a distance r(a) from axis of rotation. Settling time of particle is limited by residence time of the liquid in the ball. At the end of the residence time, let the particle be at a distance r(b) from the axis of rotation. If r(b) is less than r2, then particle leaves the ball with liquid, separation will not take place. If r(b) is equals to r2, then particle is deposited on the ball wall and removed from the liquid. So, this r(a) and r(b) we are taking two different locations within the column of the liquid, within the column of the liquid, that is from r1 to r2 distance. Between r1 to r2 distance we have taken these two arbitrary positions, so that we can do calculations. But we do not know what are these RA, RB values. Indeed, we do not want. We wanted to make sure the particles are within this range between R1 to R2 distance only, okay, so that we can do the calculation and then we can find out the required volumetric flow rate. Let us assume particles settle in the Stokes' law regime, then the terminal velocity at radius r is nothing but ut is equals to r omega square dp square rho p minus rho divided by 18 mu. This we have already derived in the flow past a particle system kind of thing. Those things when we have done settling velocity of particles under the gravity as well as under the centrifugal field. Those things we have done. So, under Stokes regime, if the particles are settling due to the centrifugal field, then the velocity is given by this expression. Now, ut is nothing but dr by dt, r is the position where the settling velocity we are calculating. So, then from here we can write dt is equals to 18 mu by omega square rho p minus rho dp square dr by r. Why are we writing? Because we wanted to find out the residence time of the liquid, so the time we have to find out here. So, now the important thing is the boundary condition. What are the boundary conditions? So, then at entry point particles we have seen, we are assumed like that they are at RA position. So, at t is equals to 0, particle is at RA position. So, at t is equals to 0, R is equals to nothing but RA, and then by the end of the residence time, by the end of the residence time of the liquid, the particle has to reach RB. That is the condition we have taken. So, at t is equals to Tt, R is equals to RB. Okay. Tt is nothing but residence time of the liquid. So, this is what we have. Now, you integrate equation number 2 and then substitute this boundary condition. So, integration of dt is nothing but t. So, applying these boundary conditions 0 to tt, we have tt, and then right hand side dr by r is nothing but ln r. So, applying the boundary conditions Ra and Rb for t is equals to 0 and t is equals to tt, we have ln Rb by Ra. Rest all other terms are independent of t and then r. Residence time Tt is equal to the volume of liquid in the ball divided by the volumetric flow rate. So, volumetric flow rate we do not know, we have to find out. So, if we find out volume, that we already have seen, V is nothing but pi b R2 square minus R1 square. So, that V if you divide by this residence time, then we get the volumetric flow rate, then we get the required volumetric flow rate. So, volume is given by pi b R2 square minus R1 square. Therefore, volumetric flow rate can be found as V by Tt. When you do this V divided by Tt and then simplify, rearrange this equation like this, then you get volumetric flow rate. Then you get volumetric flow rate like this. So, Q is equals to pi b omega square rho p minus rho dp square by 18 mu R2 square minus R1 square divided by ln Rb by Ra. Right. So, now this equation, though we have a kind of expression for the volumetric flow rate, it is not useful because this Rb and then Ra are a kind of arbitrary locations. Ra is towards the liquid surface and then Rb is towards the centrifugal ball wall, right. So, these, but they are not equals to R1 or R2 respectively. So, then this equation can be useful only when we know what is Ra and what is Rb. So, for that we do some kind of analysis now. So, let us define cut point as the diameter of that particle which just reaches the one of the distance between R1 and R2. So, we define a kind of cut diameter of the particle, so that whatever the particles larger than that cut diameter can be hitting the wall and then being separated. Less than that size may be going out along with the liquid without being separated. So, that cut diameter, let us assume that is that particle, whichever cut diameter particle, let us say dpc, we have taken the cut diameter of that particles which is being hitting the wall. So, that reaches one of the distance between R1 and R2. Okay. So, whatever the R1, R2 are there, R1 is nothing but the distance from the axis of rotation to liquid surface, and then R2 is nothing but the ball radius. So, that is the R1, R2 distance, whatever it is covering, that is R2 minus R1 is nothing but the thickness of the liquid surface. Okay. Half of that distance, if the particle is reaching within the residence time of this liquid, then that particle is going to be separated. So, if dpc is the cut diameter, particle of this size moves a distance R2 minus R1 by 2 during the settling time allowed as per this definition, right. So, distance between R1 and R2 is nothing but R2 minus R1 according to schematic. So, schematic, this is the center of axis, this is the liquid surface. So, this is R1 and then this is ball radius R2. So, now DPC is reaching off the distance of this whatever the R2 minus distance between R2 and R1. Distance between R2 and R1 is nothing but this liquid surface distance, that is nothing but R2 minus R1. We are taking this particle DPC based on the this distance, that half of this distance that particle is reaching within the liquid residence time. So, that is R2 minus R1 by 2, R2 minus R1 by 2 distance that particle is reaching within the residence time of the liquid. That is, if dPc is the cut diameter, a particle of this size moves a distance R2 minus R1 by 2 during the settling time allowed. If a particle of diameter dPc is to be removed, it must reach the ball wall in the available time, right, within the available time. What is the available time? It is nothing but the liquid residence time. So, within that time this particle has to reach the wall of the ball, that is, it has to reach the R2 distance. That means RB has to be equals to R2, right. RB is nothing but that is the one by the as per the analysis, RB is the distance, like we have this liquid surface, I am drawing again here. So, this is RA position somewhere and then this is RB position, right. The particle is moving in this direction like this. So, within the residence time this RB particle has to hit the wall. So, that means RB has to become R2, then only the particle separation will take place. Okay. So, therefore, RB has to be R2 and then RA has to be nothing but R1 plus R2 by 2, because we have taken half the distance, right. RA should be R1 plus R2 by 2 in above equation. So, that whatever the Q expression that we have developed, in that Q expression wherever RB is there you replace RB by R2 and then wherever RA is there, that RA you replace by R1 plus R2 by 2. Then we have the volumetric flow rate expression like this, and then this volumetric flow rate we call it QC. We call it QC because this volumetric flow rate is corresponding to cut diameter. Since it is corresponding to the cut diameter, the volumetric flow rate has to be QC and then D has to be replaced by dPc. Now, this one actually RB ln RB by RA. So, RB is R2 and then RA is nothing but R1 plus R2 by 2. So, then ln 2 R2 by R1 plus R2. Now, in this equation everything is known for us. Liquid interface in general is known, we can calculate even if it is not known, right. Ball radius is known, ball height is known, rotational speed is known, densities of particle and then liquid we know, particle cut diameter we are deciding, viscosity is known, everything is known. So, then you can know what should be the volumetric flow rate that you should provide, so that these particles of having size dPc or greater should be hitting the wall and being separated. Okay. At this flow rate, most particles whose diameters are larger than dPc will be eliminated by the centrifugal force, because those particles the size is slightly bigger than this cutoff diameter. So, they will be having they will be moving more towards the wall. So, there is a possibility or the chances that these particles whose size is more than dPc will be hitting the wall is more and then being separated by settling at the bottom. Okay. So, whereas the particles having smaller than dPc diameter will remain in the liquid, okay, without being separated. Okay. So, now let us say, as I mentioned already one example, if you have a 0.1 to 10 micron size particles in a liquid solution, right, and then you have a fixed dimension ball, centrifugal ball, and then if you wanted to separate the particles whose size is 1 micron or more, what should be the volumetric flow rate that you should provide to the inlet feed, you can calculate from here. So, here in dPc you substitute 1 micron, 1 into 10 power minus 6 meters, and then correspondingly the density, viscosity of all these things you substitute and then calculate the volumetric flow rate. So, whatever this QC that you get, if you provide that QC value for the feed flow rate, then all the particles which are having 1 micron or more size will be separated, but the particle size having less than 1 micron will be remaining with the liquid as in the overflow. Okay. If the thickness of the liquid layer is small compared to the radius of the ball, R1 is equals to R2, approximately equals to R2, because in general, industrial centrifuges, they rotate at very high rotational speed like 15,000, 25,000 RPM, etc. Under such kind of high velocities, the liquid, more and more liquid is being pushed towards the wall, and then this liquid interface is almost close to the wall of the ball. So, that is R1 is approximately R2. So, under such conditions, the same equation, whatever QC expression that we have derived, we can, under those conditions, what will happen if you substitute here R2 is equals to R1, approximately what will happen? Like let us say in the case where we have a kind of R1 is close to R2, that is possible in many industrial applications. So, if you substitute here, so this is going to be 0, R2 square minus R1 square is going to be very, very small, because R1 is close to the R2 value anyway, right. It is going to be very small, and then you are going to get unreliable values here from there, or very small flow rate you may get it. So, how to overcome such situation and then develop appropriate volumetric flow rate equation, so that we are going to see now. So, under such conditions, if R1 is approximately close to R2, so then whatever the settling velocity of the particle is there within the centrifugal field, that can be written as R2 omega square dp square rho p minus rho by 18 mu. Earlier we have written R here, R we have written, which is nothing but in between some location between R2 and R1 within the liquid layer, that is within the liquid layer some location R that we have taken and written previous equation and derived it. Now, in the present case, this second case, R1 is approximately R2. So, then there is no point of taking position in between these two, because they are close to each other. So, directly we can take R2. Why R2, why not R1? Because we want the particles to be separated by being hitting on the wall of the ball. Because of that one, that size R2 we are taking it rather than R1. Right. So, ut for such conditions where R1 is approximately equals to R2, we can write it as R2 omega square dp square rho p minus rho by 18 mu. And let us say thickness of the liquid layer. Now, this thickness of the liquid layer is very thin. If you draw here, now here we are having very thin layer like this. So, if this is a kind of axis of rotation or central axis, so this is your R1 and then this is your R2. Compared to R2, R1 is not very small, it is very close to each other, right. So, under such condition, the thickness of this liquid layer is also very small. So, rather writing R2 minus R1, you just designate some value S, some value S. Okay. So, now if the liquid layer thickness is S, then the settling distance for the particles of cut diameter dpc should be nothing but S by 2. Simply, as in the previous case, we have done R2 minus R1 by 2. Now, R2, R1 close to each other. So, that R2 minus R1, whatever the thin layer of liquid is there, that we are calling S. So, S by 2 we are writing. Then settling velocity we can rewrite as a kind of that distance S by 2 divided by the residence time of the liquid, divided by residence time of the liquid, that S by 2 divided by Tt, that is S by 2 Tt. Tt is nothing but residence time of the liquid within the centrifugal bowl. Now, from here you know the velocity, so volume is also known. So, then you can calculate volumetric flow rate. So, residence time is nothing but volume of the liquid divided by the volumetric flow rate, right, or volumetric flow rate is nothing but volume of the liquid divided by Tt. So, now volumetric flow rate here, from here what we can write, Qc is equals to V by Tt, and then V by Tt from this equation number 8, what we can write? We can write it as Tt is equals to nothing but S by 2 ut. So, that means 2 ut V by S, we can write it as a kind of volumetric flow rate, right. When you do this one, So, QC is equals to 2 V ut by S. So, V is the volume of the liquid that we are having inside the ball from which particles are being separated. So, that volume of the liquid V we know. This ut just now we have written it as R2 omega square rho p minus rho dp square by 18 mu S is divided by S. So, this S is there. So, this is the volumetric flow rate. If you know the thickness of the liquid layer, then you can know volumetric flow rate from this equation as well. Okay. So, but this equation is more suitable when you have a kind of very thin liquid layer where R1 is almost close to R2. Now, sigma value scale up. This sigma value is in general used to find out the scale up for the industrial applications. What does it physically indicate? Let us say physical, whatever the sigma value that we are going to do, if you get some sigma value, that indicates the area of a gravitational tank that should be provided to do the same duty that this centrifugal ball is doing. Okay. So, whatever the separation that you are doing from DPC particles, particle size greater than DPC are being all separated, right, by providing some kind of volumetric flow rate that you are doing in a ball, a centrifugal ball having radius less than 1 meter or something like that, right. That within small ball you are doing separation, but when you do this, we are going to do some problems also, we will find out sigma value. This sigma value is going to be order of 10 power 3 or 10 power 4, sometime 10 power 5 meter square. So, whatever the separation that you are doing in the small centrifugal ball, if you wanted to do the same separation in a gravity sedimentation, you have to have a gravity sedimentation tank of area equal to sigma value. Such large tank you should use. Anyway, we see the problem, but let us go into the evaluation of the sigma value. For application to industrial centrifuges, equation number 10, whatever we just derived for case when R1 is closely equals to R2 is modified as this, right. So, radius R2 and thickness S are being replaced by RE and SE respectively, which are appropriate average values of R and S for the type of centrifuge under consideration, right. So, that is one we are doing, and then what we are doing, the equation, that equation number 10 just we derived for QC, that is 2 V ut by S. In that equation we are dividing and multiplying that equation in the right hand side by the G, and then we will have a kind of terms where all the terms related to the centrifugal field are kept as a kind of one group, and then remaining terms related to the gravity sedimentation we kept as a, we are going to keep as a kind of other group, right. So, RHS of equation 10 is multiplied and divided by G, and all factors relating to the centrifuge are collected in one group, and those relating to the solids and liquid in other group to give. So, this is the equation actually, this is the equation number 10 that we have derived just now. This equation what we are doing, we are just simply dividing and multiplying by G in the RHS, and then whatever the particle solid liquid properties are there, viscosity, particle density, and then liquid density, particle size, these we are writing as a one group. Then we can see this is having a kind of G dp square rho p minus rho by 18 mu form, and then remaining terms related to the centrifuge, that is omega square RE effective, S effective, V, etc. These things, V is nothing but the volume of the liquid. So, these remaining thing we are writing as other group. So, now here what we can see, this G dp square rho p minus rho by 18 mu is what? Is nothing but the terminal velocity of the particles settling in gravity field if the settling velocity is under the Stokes regime, right. If the particles settling in Stokes regime due to the gravity field, then what is the settling velocity ut expression that we have derived previously? We have derived it as G dp square rho p minus rho by 18 mu. So, that let us indicate it as Ug, and then here in this equation in the other terms, that is related to the centrifuge terms, this 2 you keep it as it is, and then remaining terms V R E omega square by G S you write it as sigma, that is nothing but the sigma actually, that is nothing but the sigma. Okay. So, this QC we can write it as 2 sigma UG, it is not a kind of summation, this sigma is not a kind of summation, it is a kind of a symbol that has been used for this scale up purpose. Okay. So, the equation number 10 we can write it as 2 sigma UG, simply dividing and multiplying the right hand side of equation number 10 by gravity, acceleration due to gravity G, and then rearranging it. So, QC is equals to 2 epsilon UG, where the sigma value is a characteristic of centrifuge and UG is the terminal velocity of the particle under gravity settling conditions. So, as I mentioned, physically sigma is cross sectional area of a gravity settling tank of the same separation capacity as the centrifuge. As I mentioned, physically what does the sigma value indicate? The sigma value indicate the cross sectional area of a gravity settling tank of the same separation capacity as the centrifuge. Let us say take the same example, you have a liquid sample in which we have the particles like 0.1 to 10 micron size, let us assume, and then you wanted to separate all the particles having size greater than dpc greater than or equals to 1 micron, right. Then if you do the separation in centrifugal bowl, you can take a disc centrifuge of radius something like 0.5 meters diameter like that, and then get it done with by calculating that volumetric flow rate, whatever the volumetric flow rate you have to provide, that you can calculate, right. But that separation if you wanted to do in gravity sedimentation tank, then how much cross sectional area should you provide for that sedimentation tank in which the particles are settling by gravity. That information, that cross sectional area of the sedimentation tank is nothing but the sigma value, which is going to be very large in general, order of 10 power 3 to 10 power 5. Okay. We are going to see a few problems as well. So, for instance, a 0.5 meter disc centrifuge is equivalent to a gravity sedimenter with an area of over 10 power 5 meter square. You can see how much is the difference. Now, where is the ball of 0.5 radius centrifugal ball? You need, that is very small one, and then 10 power 5 meter square gravity sedimentation tank, how big it is. So, that is the other advantage of using this centrifugal separation processes. In practice, the actual capacity of centrifuge may be somewhat less than that indicated by the sigma value because of the complicated flow patterns in revolving centrifugal ball, and in some designs the resuspension of particles by an internal conveyor may also take place, but these discrepancies are not going to be too large from the calculated values anyway. So, now we see some example. The first example is about finding out the neutral zone that we have derived in the previous lecture, right. So, in a vegetable oil refining process, an aqueous phase is being separated from the oil phase in a centrifugal decanter. Oil density, aqueous phase density are given, radius of outlet for overflow of liquid, that is RB, is given. Similarly, radius of outlet for heavy liquid, that is RA, is given. So, calculate the location of the interface RI or the size of the neutral zone Ri, that we have to find out. Okay, that is the question. This question, the derivation for Ri, what we have done in a previous lecture. Okay, there we have not taken any problem, so we are taking here. So, here we need Ri is function of rho b by rho a. So, we know that Ri is function of rho b by rho a. So, rho b by rho a, if you do, it comes out 0.93798. Then Ri is equals to square root of Ra square minus rho b by rho a whole square Rb square divided by 1 minus rho b by rho a. So, then we get this value, substitute all this value, rho a, rho b values are given, Ra, Rb values are given. So, everything is known, substitute here simply and then simplify. Then Ri location is going to be 1.36917 centimeters, that is approximately 13.7 mm. Okay. Now, we go to the example number 2. What is the capacity in meter cube per hour of a classifying centrifuge operating under the following conditions. Ball dia is given, thickness of liquid layer is given, depth is given, speed is given, specific gravity of liquid and solids are given, viscosity of liquid is given, cut size of the particle dpc is given 30 microns. Then you have to calculate the volumetric flow rate in meter cube per hour. Volumetric flow rate has to be reported in meter cube per hour. We get from solution meter cube per second. In meter cube per second we get the answer, but that has to be converted in meter cube per hour. So, this rotational speed is given. So, omega you can find it out by using 2 pi n. So, that is 125.7 radians per second. So, rho p is given, rho is given, and specific gravities are given, and then we are multiplying by 998. So, then we get the kg per meter cube units density for rho p and rho. Mu is given, R2 is given, dpc is given as 30 microns. We can write it as 30 into 10 power minus 6 meters or 3 into 10 power minus 5 meters. B is given as 0.4 meters. So, R1 is required. R1 is nothing but the liquid layer thickness is given as 75 mm kind of thing, right. So, then R2 is given. So, let us say if this is the central axis of rotation, and then liquid interface is this one R1. This is R1 is given, and this is R2 is given. This is R1, this is R2. R2 is given, but R1 is not given, but this thickness of this liquid layer is given. Okay. So, from R2 if you subtract this thickness of the liquid layer, you will get R1, because in QC calculations we need R1. So, R1 is equals to 0.3 minus the liquid layer thickness 0.075 is equals to 0.225 meters. In meters I have written here. Okay. So, R2 is given, liquid layer thickness is given. So, from R2 if you subtract the liquid layer thickness, then we get R1. Then we get R1 as 0.225 meters. Assume Stokes regime or prove it as follows by obtaining K value. Actually, whatever the derivation that we have done till now, the principles, working principles we developed, they are valid only for Stokes flow regime. We have taken ut as r omega square dp square rho p minus rho by 18 mu, that is valued if the particles are settling under the Stokes regime, right. So, but the present flow conditions are within the Stokes regime or not, that we have to make sure. Then only corresponding QC equation whatever we derived, we can use it. How to find out whether the particle is settling in Stokes regime or not? We have already seen in one of the previous lecture, finding out the K value. If K value is less than 2.6, then the particle is settling in the Stokes flow regime. So, let us say this is K value calculation. This K is nothing but dp cube root of 0 delta rho by mu square. This we have already seen. So, dp is given 30 microns, rho p are known, mu are known, mu is also known. So, then when you substitute, you will get 0.316. So, which is less than 2.6. So, then it is under Stokes flow regime. So, we can happily use this QC expression without any problem. So, then QC we have developed it as a pi b omega square rho p minus rho dp square by 18 mu r2 square minus r1 square divided by ln 2 r2 by r1 plus r2. So, in this equation now everything is known. So, simply substitute and then calculate the simplifications. If you do, you will get 0.0584 meter cube per second. If you convert it into the meter cube per hour, it is approximately 210 meter cubes per hour of flow rate you have to provide, so that the particles of size 30 microns or larger can be separated from the feed liquid which is having wide particle size distribution. Okay. So, whatever the particles having the size less than 30 microns would be retaining in the liquid only and going out along with the overflow liquid if you provide this flow rate. Whereas, all the particles having size greater than 30 microns will be reaching the ball wall within the residence time of the liquid and then being separated. Okay. Now we take another example. A viscous solution containing particles with a density rho p is equals to 1461 kg per meter cube is to be classified by a centrifugal ball. So then solution viscosity density are given, radius of ball is given, radius of free liquid surface R1 is directly given in this problem, ball height B is also given. So calculate the cut diameter if the flow rate is 0.002832 meter cube per hour and then rotational speed is 23,000 rpm. So it is the other side of the previous problem. Previous problem dPc is given, flow rate we have to calculate. Now dPc we have to calculate and then flow rate is given. So omega 2 pi n by 60 comes out to be 2410 radians per second. QC is given in meter cube per hour, so that we have to convert into the meter cube per second. Then it comes out to be 7.87 into 10 power minus 7 meter cube per second. So then QC is nothing but pi b omega square rho p minus rho dp square by 18 mu r2 square minus r1 square divided by ln 2 r2 by r1 plus r2. This equation we have derived. So in this equation everything is known except the dPc. Except the dPc, everything is known in this equation. So substitute all these values and then find out this dPc. So then dPc you are going to find it out as a 0.75 microns. So that means if you provide 0.02832 meter cube hour of a feed flow rate, then particles of size greater than or equals to 0.75 microns will be separated for this flow conditions and then for this fluid properties whatever given in this problem. Okay. Another example problem. In a test on centrifuge, all particles of rho p 2800 kg per meter cube and dp 5 microns, sphere volume equivalent diameter is given, were separated from suspension in water feed at volumetric throughput of 0.25 meter cube per second. Q is given, dp is given, rho p is given here. Calculate the sigma value. Sigma value we have to find out. Okay. What will be the corresponding size cut for a suspension of coal particles in oil fed at the rate of 0.04 meter cube per second when the sigma value is there. Okay. Correspondingly the same thing is used like for this suspension of coal particles are there. So then what should be the corresponding size cut, that we have to find out, and then it is given that assume Stokes law applicable. So we do not need to find out K value. So first part of the solution is finding out the sigma value, that is QC is equals to 2 sigma UG, that we already know, and then if you expand this equation 2 V omega square RE by G SE, and then UG is nothing but dP square rho p minus rho G by 18 mu. So here we have to find out this sigma value. Q is given. Okay. If you wanted to use this part of the equation, you need to know omega, S, V and all these things which are not given. So then what you can do, you can use this equation, that sigma is equals to QC by 2 UG, because UG is nothing but this part that you can calculate, because dP is given, rho p, rho, mu are given. So sigma is equals to QC by 2 UG, and then solution is like it mentioned like the viscosity and then density of the solution are same as of that water. So UG is nothing but G dP square rho p minus rho by 18 mu, and then and for water rho is 1000 kg per meter cube, mu is 10 power minus 3 Pascal second at the given conditions. So then UG you can find it out as 2.45 into 10 power minus 5 meter per second. So now QC is known. Now UG also you calculated, you submit here. So then sigma value you get it as 5.102 into 10 power 3 meter square. So what does mean? Whatever the separation that you are doing by using the centrifugal ball, if you wanted to do the same separation by gravity sedimentation tank, then you have to have such big gravitational sedimentation tank whose cross sectional area is 5.102 into 10 power 3 meter square. Such big sedimentation tank one should provide. Okay. Second part of the question, if the sigma value is this one and then that ball is used for some other separations like coal suspension, then what would be the cut size? Okay. What will be the corresponding size cut for a suspension of coal particles in oil fed at the rate of 0.04 meter cube per second? The Q is also different now, right. So, then here we have to find out dP. Okay. So, the same expression we are going to use here also. Ug is nothing but Qc by 2 sigma, right. So, because the other equation, that equation number 10 for Qc in terms of R1, R2 and all that V etc., omega etc. are not possible, because omega is not given here in this equation. Omega is not given in this equation. So, what we do? We calculate dPc by different approach. What we do? From using this Qc is equals to 2 sigma Ug, right. So, new flow rate 0.04 meter cube per second is given. Sigma we just calculated it as 5.102 into 10 power 3. From here, for this case we calculate Ug. Previous case was for different condition. For these conditions, now you can calculate Ug here by Qc by 2 sigma, and then now this you equate by G dP square rho p minus rho by 18 mu. So, then if you put it here C cut diameter. So, whatever the particles of this dPc you will get, right, all those particles are size greater than this dPc will be separated. So, this approach we are going to follow. So, dP square, this Ug is nothing but G dP square rho p minus rho by 18 mu. From here we can write it as dP square is equals to 18 mu Ug divided by G delta rho, right. So, then from here you get dP square is equals to 1.63 into 10 power minus 10, and then dP you are going to get it as approximately 1.2767 into 10 power minus 5 meters, or approximately 12.7 microns. Okay. This way also we can do it. We are doing this way because the omega etc., those information are not available. Another example problem, a liquid detergent solution of 100 Cp viscosity and 0.8 gram per cc density, centipoise, viscosity is given in centipoise, is to be classified of fine Na2SO4 crystals of density 1.46 gram per cc by centrifugation. Pilot runs in a laboratory super centrifuge operating in 23,000 rpm indicated that satisfactory classification is obtained at a throughput of 5 lb per hour of solution. This centrifuge ball has 7 3/4 inch long internally with R2 is equals to 7 by 8 inch and R2 minus R1 19 by 32 inch. This is 7 3/4 inch, that is 31 by 4. Determine dPc for this separation. So, Qc is given in lb per hour. Let us convert it in centimeter cube per second. We will do this problem in CGS units. Okay. So, when you convert, you will get this value. B is given. So, the 7 3/4 inches. So, in centimeter it is 19.685 centimeters. R2 is 2.2225 centimeters. R2 minus R1 is 1.5081 centimeters. So, R2 minus 1.5081 would nothing but R1, that is 0.714375 centimeters. Mu is 100 centipoise. So, that is 1 gram per centimeter second. Okay. So, then omega is the other requirement, that is n is to 23,000 rpm is given. So, omega comes out to be 2410 radians per second. So, now everything is known in this Qc expression, except the dPc. So, this we can find it out. So, Qc we have this expression, and then Qc is given as 0.7875 centimeter cube per second. Okay. So, 5 lb per hour, that is 0.7875 centimeter cube per second. So, now here you substitute all these values except this dPc which is not known, and then simplify this equation, you will get dPc is approximately 1.08 into 10 power minus 4 centimeters. This is how you have to solve the problems using the centrifugal separation principles. Okay. Now, we see a few basics about the cyclone separators. Cyclone separators are conical shaped ball vessels like this, right. So, here what happens, the fluid which is containing particles is being introduced into this vessel at high tangential velocity, right, and then when this hits this surface, and then because of the conical shape, this fluid rotates in this direction, vertex downward that will be formed. When the fluid reaches down, then upward liquid vertex will be found like this, and then clear liquid will be taken from the top. Whereas the particles, when this fluid rotates down like this, particles being hit on the conical surface, conical vessel surface here, and then being separated and collected from the bottom. That is the principle. Simply, that is the principle of the cyclone separator. For this equation, for this case, we are going to develop the required equations. Assume that particles on entering a cyclone quickly reach their terminal settling velocity, that is important. Particle sizes are usually so small that Stokes' law is valid, because these kind of separation cyclone separators we use in general to separate micron size particles from the dust laden air or gases, something like that, right. So, those particles in the air are the gaseous effluents from the industries have the particles of very small size of micron size. So, such micron size particles will obviously settle in Stokes region, because their settling velocity would be rho, because their settling velocity would be low. Why? Because their particle size is order of 10 power minus 6 or even small in meters. For centrifugal motion, the terminal radial velocity VTR, right. So, let us say the now here what happens when the fluid comes in here and then rotates going down like this here as a kind of vortex form, because of the vortex forming here, right. There are two forces are there. One is the centrifugal force, because this fluid is rotating, another one is the gravity field force is also there. Okay. So, whatever the terminal velocity for the particles due to the centrifugal force, that we call designated as VTR. So, at some location R, VTR is nothing but R omega square dp square rho p minus rho by 18 mu. This we already derived in one of the previous lecture, right. So, the settling velocity of particle in centrifugal field under the Stokes regime is VTR. Now, we designating as VTR, previously we have written as UTC kind of thing. So, now we are writing VTR, it is nothing but R omega square dp square rho p minus rho by 18 mu, and then we know that tangential velocity V tangential is nothing but R omega. So, in place of this omega, if you substitute V tan by R, then we have this equation like this, right. Here what we are doing, this equation, in this equation in place of omega, we are writing V tan by R, okay, V tan by R. So, V tan square by R square should be there, and then remaining one R term was already there here. So, this R square of the R term is cancelled out, then further we are multiplying and then dividing by G. So, that this part G dp square rho p minus rho by 18 mu is nothing but terminal velocity of the particle settling under the gravity field, and then Stokes regime is valid, right. Under the Stokes regime, if a particle is settling in a gravity field, then the settling velocity is nothing but G dp square rho p minus rho by 18 mu, that is ut we have written previously. Now, we are writing Vt, just change of symbols only, and then what are the remaining terms? V tan square by Gr, V tan square by Gr. Now, from this equation what we understand, if Vt is higher, so that is the settling velocity of the particle, though it is in the Stokes regime, but upper end of the if it is goes towards the upper end of the Stokes regime, right. So, then this VTR is going to be further greater, VTR, that is tangential velocity, tangential radial velocity for that particle due to the centrifugation, that is going to be much higher because Vt is increased. So, because tangential velocity is anyway that larger, and then G and R are all are positive values. So, then it will further Vtr is going to be further larger for a higher Vt value. That is what we see now. Okay. Higher the gravitational terminal velocity Vt, the greater the radial velocity Vtr, and the easier it should be to the particles to settle at the wall. Okay. So, that means if you want particles to be settling at the wall, you should provide a upper end of a gravitational terminal velocity, okay, for those particle size. Right. Now, so I just rewrite once again so that to avoid confusion. Vtr is nothing but settling velocity of particles in centrifugal motion. Vt is nothing but settling velocity of particles in gravity field. Okay. And then V tan is nothing but tangential velocity. Which is nothing but R omega. Okay. But in general, getting this Vtr information directly is difficult because you need to know tangential velocity, you need to know the gravity settling velocity, and then R position, what R position, and all those things, right. Evaluation of radial velocity, that is Vtr, is difficult because it is function of gravitational velocity, gravitational terminal velocity, tangential velocity V tan, and position radial position R, right. So, that is the reason we have a kind of empirical equation often used of this form. This is empirical equation, not the derivation, it is empirical equation. Vtr is equals to B dp square rho p minus rho by 18 mu r power n, whatever this r omega square is there, that one, and then this here r are there, they are modified such a way that they are some kind of empirical constants, in terms of empirical constants are written. Okay. So, this n and b are nothing but empirical constants. So, smaller particles have smaller settling velocities according to this equation obviously, and do not have time to reach the wall to be collected. So, obviously they leave with the exit gas in cyclone separator without being separated, whereas the larger particles are more readily collected at the wall and being separated from the bottom of the cyclone separator. So, these are the few details about the cyclone separators. Now, we go to the hydrocyclones. Cyclones are also used for the liquid solid separations also, they are known as the hydrocyclones in general. So, in hydrocyclones or hydraulic cyclones, separation is effected in the centrifugal field generated as a result of introducing the feed at high tangential velocity into the separator. The same way, exactly the same way the process happens, whatever for the cyclone separator. Okay. Pictorially also we will see now in the next slide. Hydrocyclones are sometimes used as thickeners, but more commonly used as classifiers as well. It may be used for separating particles suspended in a liquid of lower density by size or density, or more generally by terminal settling velocity differences. Removal of suspended solids from a liquid, for that purpose also they are used. Separating immiscible liquids of different densities, for that also used, and then also used for dewatering of suspensions to give a more concentrated product. And then sometimes breaking down liquid or gas liquid dispersions, for that purpose also these hydrocyclones are used. Removal of dissolved gases from liquids are also being separated by these hydrocyclones. So, pictorially if you see, so these are also kind of same like cyclone separator like this, they are have a kind of a conical column like this. Okay. So, now the feed comes in here at high velocity like this, and then this hits the wall, and then because of that one it undergoes a kind of rotational motion like this, and because of this rotational motion what happens, centrifugal field will be developed. So, this feed containing the particles, they will be going through under kind of rotational motion like this, okay. And then in this process what happens, this feed whatever having the particles, it is having the particle also, those particles being hit on the walls of this container cyclone separator and then settling at the bottom will be taken as a kind of underflow, right. So, once this feed reaches the bottom like this here, what happens, almost clear liquid generate a kind of secondary vortex which moves upward through the center of this larger vortex like this, and then moves like a overflow from here. So, there are two vortex, one is the bigger vortex that is moving down because of the high tangential velocity feed coming in, and then once the particles, most of the particles are being separated while this fluid is going down in a vortex motion like this. So, these particles are being hit on the cyclone walls and then being separated. So, by the time that feed reaches the bottom, most of the particles are being separated. So, that will be having the lower density kind of thing, and then those liquid will move up with a kind of as a kind of inner vortex, and then taken away as a kind of overflow like this. Okay. This is the hydrocyclone process, how it works. Feed enters tangentially at high velocity near the top. Liquid follows a spiral path near the vessel wall, forming a strong downward vortex. Large or heavy solid particles separate to the wall and are pushed downward and out of the cyclone as a slurry or paste. A variable discharge orifice controls the consistency of the underflow at the bottom. Most of the liquid goes back upward in an inner vortex and leaves through the central discharge pipe known as vortex finder. In hydrocyclone, it is not possible to have both good solids removal and a high underflow concentration. Thus, depending on the function of the unit, the shape of the hydrocyclone is in general modified. So, for classifying purpose, you may have a kind of this kind of hydrocyclone where this top section is like this, and then the conical section is a kind of smaller one like this. Conical section is the smaller one, the other section is a kind of bigger one. That is what we have in general if you want to have a kind of classifying separation. If you want this hydrocyclone to act as a kind of thickening, so that virtually all particles being separated for the liquid, then you should design this hydrocyclone such a way that their conical section is bigger compared to the other this section, fluid entering section. Okay. So, that is the difference. So, as per the requirement, these hydrocyclone designs are modified in general. In thickening operations with nearly all solids removed from the overflow, the underflow concentration must be less than 12% by volume. When hydrocyclones are used for classifying, the underflow can be more concentrated, up to maximum of about 50% by volume for slurries of limestone or coal. In hydrocyclones, the pressure drop varies with the feed rate, raised to a power of between 2 and 3.3. For dilute feeds, the cut diameter varies with the 1.5 power of the cyclone diameter. These are some kind of experimental observation. From the experimental observation, after doing some kind of curve fitting empirical correlations, these numbers are achieved. So, for a given pressure drop, a small diameter gives better separation than a larger one. Therefore, hydrocyclones are in general small in size. Cyclone separators in general we have seen very big sizes in general in industry, but these hydrocyclones are in general small in size. How small? In general, they range in diameter 10 mm to 1.2 meters in general. So, they can be as small as 10 mm hydrocyclones. To handle large flows, many small hydrocyclones are connected in parallel with as many as 480 10 mm units manifolded in a single assembly. Such small 10 mm hydrocyclones are taken, and then
such small 10 mm hydrocyclones you take, and then around 480 number, those many number of 10 mm hydrocyclones are in general manifolded in a single assembly for or in order to handle large flows. Cut size is a weak function of the pressure drop. For dilute feeds, it varies with minus 0.25 power of the pressure drop. Hence, large pressure drops are not economical in general for hydrocyclones. This is about a few basic details about hydrocyclones. Then coming to the references, we have several references for this course, all are listed here, but primarily this lecture is prepared from this reference book, Unit Operations of Chemical Engineering by McCabe, Smith and Harriet. However, some problems are taken from this book, Richardson and Harker, as well as Ortega and Revas, and then Giancopoulos. A few problems are also taken from this book, Faust et al. Thank you.